Bonding and electronegativity. The periodic table that you see right here in this red box I'm drawing, it's actually on the second page of your handout. I just wanted to be sure we could look at it here, so I've moved it here where we can find it easily. So, what is electronegativity? Electronegativity is the attraction that an atom exerts on a pair of electrons involved in a bond. So if you have hydrogen and hydrogen and they're sharing electrons in a bond, because they have the same electronegativity, 2.1, 2.1, they are going to pull, this hydrogen will be attracted to this pair of electrons with the same force that this hydrogen is attracted to the pair of electrons. That's electronegativity. So you can see that as we go across a period on the periodic table, starting like this and moving across, what do you see happening to the electronegativity? Well, you see the electronegativity increase. It goes from, say, 0.9 up to 2.5 if we're looking in this particular row, this particular period on the periodic table. Now, as you go down a family, notice here we're looking at 2.1, 1.0, and you see that trend as we go down. So as we go down a family, we decrease in electronegativity. Now, what that really means here is if we look at this, get this table cleaned up a little bit, if we look at this periodic table, the lowest electronegativities are down here in this corner with the metals at the lower side of the metals, and the highest electronegativity is up at this corner. So really the trend in electronegativity is an increase up at this corner and a decrease at this corner. And the farther apart these atoms are, the greater their electronegativity difference will be. So we'll find that this electronegativity is what tells us, are electrons going to be shared between atoms, or are electrons going to be transferred from one atom to another? Remember, if they are shared, it's a covalent bond, and if they are transferred, it is an ionic bond that will be formed. So we're looking here at number 4 on your worksheet now, looking at a regular periodic table, ignoring the periodic table that's up here, although we're going to use it. We're just not going to bother to focus on the numbers. Circle the element with the following pairs with the greatest electronegativity. So we're looking here at A. Which element has the greatest electronegativity? Will it be barium, or will it be astatine, which is right here? And just based on our trend, we know that if we go across the period, we'll get to greater electronegativities. So this must have the greater electronegativity of that pair. Nitrogen and phosphorus, which one has the greatest electronegativity? Nitrogen and phosphorus. Of course, if we go down, as we go down a family, we get to lower electronegativities. So the greater electronegativity is going to be the one that's higher on the periodic table. Chlorine or sulfur? Well, here's chlorine. Oh, we got to get a pen to write with. There's chlorine. Here's sulfur. They're side by side. And as we go left to right, we get to bigger and bigger electronegativities. So the chlorine is going to have a larger electronegativity. Now I want to remind you that these elements are all nonmetals. That's what this line is for. This dark zigzag line separates metals from nonmetals. And so in the next problem, question number 5, they're saying which of the two types of elements, metals or nonmetals, form the following types of bonds? Well, keep in mind that if your atoms are far apart on the periodic table, like metals and nonmetals, we're going to have an ionic bond because the electronegativity differences are going to be larger. But if we're looking at covalent bonds where electrons are shared, in covalent bonds where electrons are shared, the electronegativity differences are small, and that means we're going to just have nonmetals paired with other nonmetals. Those are going to be covalent bonds. Things like oxygen combined with another oxygen. They're shared equally, going to be a covalent bond. Carbon combined with oxygen, covalent bond. Metallic bonds are formed when metals combine with other metals. So if we were to look at it, there are a lot of examples we could put here. I'm just going to throw in a couple of examples like hydrogen combined with another hydrogen form a covalent bond, or oxygen combined with another oxygen forms a purely covalent bond. Now, I really wish they had used the word, instead of purely, they had used the word non-polar, because that's the word that most people prefer. And another example of a non-polar covalent bond would be the bond between two nitrogen atoms that might look something like that. What do you call this kind of bond? Non-polar covalent bond. So what is a polar covalent bond? A polar covalent bond is when the electronegativity gets a little bit larger, like maybe the difference between atom A and atom B gets to be a difference of maybe 0.5 if you just write down the two electronegativities and find the difference. One example of this might be like the bond between hydrogen and oxygen that you would find if you looked at water. Because if you looked at that bond between hydrogen and oxygen in water, you would find hydrogen as a electronegativity of 2.1. Oxygen, I think, is 3.5. Look that up and check. I hope I'm right. Okay, I better look at here. Oxygen is 3.5. So the electronegativity difference here is a difference of 1.4. And that's large enough to be polar covalent, but small enough to still be that screen really messed me up. Small enough to be still covalent rather than ionic. What is the range of electronegativities that fall into polar covalent? Well, you're going to find most books tell you if that electronegativity difference is greater than 0.5, it's going to be polar. The place where the books often disagree is where to draw this line. At the bottom of the page, on the table that's at the bottom of your page here, you'll see that polar covalent, according to this particular table, is between 1.7 and 0.5. That's the electronegativity difference between atoms in a polar bond. What is an ionic bond? An ionic bond is where the electrons are transferred. So see if we can make that window stop popping up. What's an example of a ionic bond? Well, if we have a sodium and its electronegativity is so small, and we bond it with chlorine, whose electronegativity is so large, the sodium will completely lose its electron and the chlorine will pick it up. We have a transfer of electrons, and that transfer of electrons forms an ionic bond. Ionic bond. Taken, not shared. The greater electronegativity difference of an ionic bond. What is the electronegativity difference usually considered to form this? Well, 1.7, a difference of 1.7 between the two atoms. Or if you look at other textbooks, you may find that they draw that line somewhere around 2.1. You're going to find it in various various values depending on which textbook you happen to look at. So let's move real quickly to your second page. Problem number 10 says to do two things here. In each pair, so if we're looking here at problem 10A, you see two pair, carbon and oxygen, carbon and nitrogen. It says to do two things. Use an arrow to show the direction of the polarity. Well, if you look at this, oxygen has a greater electronegativity, so we're going to do that. Nitrogen has a greater electronegativity than carbon, so we're going to do that. We could draw this funny little symbol that it talks about that's actually a lowercase delta, and that means a partial negative and a partial positive because this is a polar bond. Now, which one is more polar? Well, if we're looking at carbon combined with nitrogen or oxygen, which one has the greater distance from each other? Well, carbon is further from oxygen than it is from nitrogen, so this will be the greater electronegativity difference will be between carbon and oxygen. Look at one more of these. We're looking at phosphorus bonded with chlorine or bromine. So we're looking at, here's phosphorus, and is it going to be more electronegative if it's combined with bromine? Oops, where's my pen? I was just trying to do a different color. Bromine, I missed it. Bromine compared to chlorine. Well, this is, in some of these cases, it may just be easier to look at the actual electronegativities. 2.1 for phosphorus, and for chlorine, 3.0, and for bromine, 2.8. So we can see there's a larger difference in this example. Now, in both of these, the positive charge is closer to the phosphorus, and the negative charge, or the electrons, are pulled closer to the bromine. And I think that's how the rest of those should look. Check your answers. So you'll want to be sure and look at each one of these. Carbon is 2.5, and hydrogen, give myself some space to write here. Where was I? Carbon is 2.5, hydrogen is 2.1, so the greater electronegativity is the carbon. Does that look right for the rest of those? So for number 12, we're going to use the periodic table that's up at the top of the page, and we're going to see we're going to write those down. So for sodium, that is going to be 1.0. For chlorine, that's going to be 3.0. Now the difference between those is a difference of 2.0. And that difference of 2.0, if we look at the bottom of the first page, anything larger than 1.7 on this particular system is going to be ionic. So this bond between sodium, the bond between sodium, get this ready here, the bond between sodium and chlorine is going to be ionic. Looking at B, we have carbon and oxygen. Carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. And that's a difference. The difference between those two numbers is a difference of 1.0. And if it's between 0.5 and 1.7, it's going to be polar covalent. So I bet you can go on and do the rest of those. Now here in E, we see an example where we actually have a metal, magnesium, bonded to hydrogen, and in that case the electronegativity difference is low enough that it's still going to be classified as a polar covalent bond.